Hello, this is Matt Roscoe here at the University of Montana with a lecture on section 3.1 of our textbook in number theory. It's on primes and their distribution. So I'd like to go over a quick historical note about primes and then go ahead and review the definition of prime number and then talk about a number of theorems about primes. And then probably the big result of the chapter is the fundamental theorem of arithmetic, which I won't prove, but I'll give you a worksheet that you can use as a critical tool to try to understand the proof of the theorem. And then we'll end with one profound implication of the FTA, and that is the birth of irrationality. Okay, so historically, prime numbers are kind of first mentioned by Euclid. They're in Proposition 14 of Book 9 of the Elements, which means that they're fairly late in the text, one of the sort of non-geometric portion of the book. And here's what Euclid says in that proposition: if a number be the least that is measured by prime numbers, it will not be measured by any other prime except those measuring it. Which at first sounds like a pretty strange result, but let me see if I can explain it to you a little bit more. So I'll turn over to my desk and talk a little bit about this. So what did Euclid mean by measuring? So here's a Euclid example. Euclid's notion of primes. The first thing you need to know is what does he mean by measure? So what does measure mean here? So you have to understand that the Greeks, had a preference for geometry. So measurement was conceived of, as sort of literally number lines with numbers. So let's give an example. If the example I give you is 12, then the question is, what can we use to measure 12? So if we kind of think of 12 as a number line, say this length, right? Let's say that's 12 units long. And then the question is what can I use to measure that number's length? And one thing you could certainly use to measure 12 would be 2. You could use 2's to measure 12 because 6 of those 2's will, I guess, add up or be used to iteratively measure 12. Of course, another thing you could use to measure 12 that's prime would be 3's. So those would look something like this, I guess. And those 3's could be used to measure the segment of length 12. I mean, of course, what we know today is what this really means, or I guess what we think of in our more arithmetic thinking world is that 12 can be measured by 2 because 2 times 6 is 12, right? And 12 can be measured by 3 because 3 times 4 is 12, right? So, so we can say that 12, I'm going to just write it as, can be measured by 2 and 3. So the primes 2 and 3 can be used to measure 12. So Euclid's proposition says something about, well, if a number is the least number that can be measured by primes, then it is divisible by exactly those primes that measure it. So let's take a look at what other numbers can be measured by 2 and 3. So other numbers that can be measured by 2 and 3, if we think arithmetically, well, what we're really talking about is any multiple of 6, right? So certainly 6 can be measured with 2 and 3, 12 could be measured, 18 could be measured, 24 could be measured, 30 could be measured, 36 could be measured, right? 42 and so on, right? So others that could be measured by 2 and 3 is this list, right? And there are no others in between. And Euclid says, well, if you're the least in this list, then you can only be measured, right, by the primes that measure it. So in other words, the least number, 6 can only be measured by 2 and 3. And of course, you look at these things and you think, well, 12 can only be measured by 2 and 3. 18 can only be measured by 2 and 3. 24 can only be measured by 2 and 3. But 30 is a number in the list that could be measured by 5, right? 36 is 2s and 3s. 42 is a number in the list that could be measured by 7, and so on. And really what you're seeing here is this is 6 times 1 times 2 times 3 times 4. So 5 is the first time where we get a non-2 or 3 factor. Times 6, that's a 2 and a 3. Times 7, so 7, right? 8 won't give us any new non-measurable by 2 and 3. 9 won't either, but 10 will. So the next one, 60, will also have a factor of 5. So I guess this is sort of Euclid's theorem. He says if you've got the least number in a list that can be measured by 2 primes, then that number will always be measurable only by the 2 primes that measure it. It's kind of an interesting notion. Some people claim that this is sort of a baby fundamental theorem of arithmetic. We'll talk about that a little bit later. So what is a prime number? The definition for prime number is varied, but the one that your textbook author uses is this one. He says an integer p greater than 1, strictly greater than 1, is called a prime number, or simply prime, if its only positive divisors are 1 and p. An integer greater than 1 that is not prime is termed composite. So one thing to keep in mind, great confusion about the number 1, whether it's prime or not, because of course 1 is divisible by 1 and itself. But the idea here is that the number has to have 2 distinct factors, 1 and p. So 1 is disqualified in that case because it only has a single factor, 1, and itself, which is 1 as well. So 2 would be the smallest prime, and so on. So here's a theorem. Let's start talking about theorems about primes. If p is a prime number and p divides a times b, then p divides a, or p divides b. So this is one of the unique things about primes, is that we can use them, I guess, to split up products using an or statement. So when divisibility is designated, I guess, when p divides a product. So let's go ahead and prove this, and I'll switch over to my desktop here, and let's take a look here. So our hypothesis, oops, that's no good. Our hypothesis is that if p is prime and p divides ab, then p divides a, or p divides b. Okay, so we proceed directly here. Okay, let's see. Let's just assume if p divides a, then we are done, right? If p divides ab and p divides a, we're done. So let's just say if p does not divide a, then what do we know? Then the GCD of a and p must be 1, right? Because of the fact that if p is not a divisor, then they share no common divisor. So its GCD must be 1. And so by Euclid's lemma, we get what? Well, if the GCD of a and p is 1 and p doesn't divide a, then p must divide b, right? Which is what we set out to prove. And that's it. That's a fairly straightforward proof, but it's fairly deep in its implication. You know, we start out with, well, we assume that p divides both of them. If P divides A, then we're done. So we're kind of without loss of generality. We're showing that if it doesn't divide one, it must divide the other. So if P divides A, we're done. If it doesn't divide A, then the GCD of A and P is 1. You should really think about that now. So if it doesn't divide A, right, then the GCD has to be 1. And the reason that's true is because the definition of prime number, right? The only two things that divide P are P itself and 1. So the GCD of A and P can be only one of two things. It can either be 1 or it can be P itself, right? Because the divisor has to divide both P and A, and if it divides P, it's either 1 or P. And then Euclid's lemma immediately provides us with this result. So this is one of these places where Euclid's lemma this is kind of, in my opinion, just a re-expression of Euclid's lemma in light of primality. So quick and easy proof. Let's go ahead and go back and talk about some other. Another corollary to this theorem is that if P is prime and P divides some sequence, some product, I guess, of n terms, then P must divide one of the terms in this product for some k, where k is between 1 and n. So it's just one of these a sub i's or a sub k's. Let's just make sure you understand this through a quick example. So here an example would be, let's say 3 divides some sequence, some product I should say, let's say 5 times 7 times 8 times 9 times, I'd say 11, okay? So if 5 divides one of these, then, or excuse me, if 3 divides one of these, then 3 must divide one of these, right? And of course you can see the one that it must divide. It must, in this case, it divides 9 and 9 alone. Now that doesn't mean that it couldn't divide more than one, but it must divide at least one of these terms in the product. And I guess you can see that's true because in order for 3 to divide one of these, I guess in order for a factor of 3 to exist over here, then it must be contained in one of these numbers, and can't be built of two numbers because of the fact that 3 doesn't have two factors. It only has one in itself. So there must be a 3 as a factor in one of these terms. Again, it's relying on the definition of primality. You know, of course, we could make a different statement here and show that a counterexample. You know, 6 certainly divides 5 times 7 times 8 times 9 times 11, but 6 doesn't divide any of these individually. And I hope you see the difference here, right? Here the 6 has a factor of 2 and 3. You can get a factor of 2, let's say, from the 8 and a factor of 3 from the 9 and put them together and ensure that 6 does divide this number. But that doesn't mean that 6 divides one of these individual terms in the product. A similar corollary that's really similar to the last one, if P, Q1, Q2, Q3, all the way up to Qn are all primes, and we say that P divides the product Q1, Q2, Q3, Qn, then P has to be equal to one of these Q sub k's, where k is one of the indices indicated from 1 to n. So here the idea is just a little bit simpler, I think, than the last one, and that is this. Let's say if 3 divides a sequence of primes that are all multiplied together, let's say 5 times 7 times 11 times 29 times, I don't know, let's pick a few more, 17 times. But you can see that certainly 3 doesn't divide 5, it doesn't divide 7, doesn't divide 11, doesn't divide 29, doesn't divide 17. So one of these things has to be actually equal to 3 if these are all prime. So that's what's I guess important here, is that if these are all primes, then one of them is equal to 3. Well, here's the big result of the chapter, and it's that every positive integer n greater than 1 is either prime or a product of primes, and this representation is unique apart from the order in which the factors occur. Okay, so this is kind of the big foundational theorem, we almost say, of number theory, and it explains so much about numbers that it's given the term fundamental in front of the theorem. There are very few theorems in mathematics that carry this term fundamental. There's a fundamental theorem of arithmetic, which we're looking at here, a fundamental theorem of calculus, right, which we're looking at here. There's a fundamental theorem of algebra as well. So these are all foundational theorems to whole branches of study. So no number theory course would be complete without addressing this theorem right up front. Um, let's just take a look at what it means practically, and then we'll talk about the proof. Um, so the FTA, what it means is if we pick any number, let's say 72, then we can re-express 72 as a product of primes, and that expression is unique to 72 and it cannot be expressed for any other number in the same way. So one way we're taught to do this in grade school is, to do these factor trees where we ask the question every time we break it into two factors whether or not the two numbers are prime. In this case, neither are prime. 2 and 4, well, this one is prime, it's 2. 4 is not prime, but it can be written as 2 times 2. 9 is not prime, but it can be written as 3 times 3, and those are both primes, right? So what does this tell us? This tells us that 72 can be written as 2 times 2 times 2, or 2 to the third, times 3 squared, and that this expression here, this prime product expression of 72, is unique to 72 up to the order in which we put the factors. So in other words, we could write it that way. We could also write 72 as 3 squared times 2 to the third. We can also write 72 as 3 times 2 times 3 times 2 times 2. So this ordering of the multiplication of the prime factors is the only thing that's non-unique. So I'd just like to show you that there's also a way that in Europe that these prime factor trees are worked. So one way that Europe does it is to do sort of this T diagram. And you ask yourself, well, is 72 divisible by the smallest prime, which is 2? And indeed it is. So you write a 2 down here and you divide it by 2 and get 36. And then you ask the same question each time. Is it divisible by the smallest prime? 2. Yes, it is. So that's 18. Is it divisible by the smallest prime? 2. Yes, it is. So that's 9. Is it divisible by the smallest prime? 2. No, it's not. So then you ask, is it divisible by the next smallest prime, which is 3? And yes, it is, and it's 3. And when we arrive to a spot where we get a 1 in this column, then this is, of course, the prime factorization. And what's nice about it is it's written in ascending form since we started with the smallest and went to the biggest prime. So it would be 2 to the third times 3 squared. This is often called the lattice method. Sometimes more successful in decomposing prime. Kids are more successful in decomposing numbers into their prime products this way because it's more systematic than the tree diagram thing. One other thing that you should be made aware of course, is that this tree diagramming could have broken out in a different way, right? We could have said something like, well, instead of 72 being 8 times 9, I could have said it's 2 times 36, right? And often kids will think, well, I'm going to get something different here if I start the tree differently. But of course you don't, right? You get 9 and 4 here, and 3 and 3, and 2 and 2. And so again, this implies that 72 is equal to 2 to the third times 3 squared. So this is one important, for you math ed majors, one important realization that needs to be shown directly to students is that no matter which way you start up here, you always end at the same leaves, even though the branching might be different. And the leaves, of course, are the prime numbers. Well, at this point, I could sit and do this, the proof of this theorem for you, but I thought that'd be more, I guess, more informative for you to pick apart the proof that you have in your book. So what I've done is I've on the website provided you with a PDF of the proof presented in your book, but that is missing a few pieces. So I'll show you what it looks like. It looks like this. You've seen me do this in class before. I've copied it larger from the text, and so you're missing a few things. You're missing something here, another star here, so you're missing something right here, and another star here. You're missing a whole line right here, and and then one thing I really want you to concentrate on when you take a look at this and do this in your own on your own is to really think about, why is this particular box statement true? Because I really feel like the whole proof relies on that particular box. So, well, make a thought bubble over here and explain why this is true. Um, and and then, yeah, go ahead and review the whole theorem. I'm going to go ahead and stop this first video here and ask you to go ahead and complete this on your own. And then crack your book and take a look and see if you got it right. And we'll start video 2 after this.